Welcome to the video on impulse. We're going to have a look today at applying concepts of impulse and impulse graphs to a long jump performance. So just remind you that impulse, first of all, is, do that a little bit better, is F times T. So impulse equals F times T. So that is, impulse is a product of force and the time period over which that force is applied, and we obviously can relate this quite closely to Newton's laws as well. So if we actually have a look at this performance of the long jump, what we can identify here is that on our curve we have got above the zero line a positive impulse and below the zero line a negative impulse. So make sure that when you're answering questions with a curve like this, anything below that zero line you consider to be a negative impulse, still acceleration is going to be taking place, and anything above the curve, in this case the green lined area, is a positive impulse curve. So that is again acceleration taking place, but in the opposite direction from the negative. So let's look at the first stages of this, A through to B. In our long jump performance here, we are saying that no impulse is being applied to the takeoff board. So in this A to B area, which I'll quickly kind of circle in here, this A to B area, no impulse is being applied to the takeoff board. So what we can of course assume here is that Newton's first law, N1, applies, and that essentially here the body is at rest. There is no acceleration upwards or downwards. In fact, we have a net impulse of 0, and therefore acceleration is not taking place, or in other words, the jumper is stationary in a vertical acceleration consideration. So they are not accelerating vertically upwards or downwards. We also need to remember that when we're calculating an impulse on a graph, it is the area under the curve that we calculate. So for example, the green dotted area between C and E, we could actually calculate this, and we can do that in the form of a triangle by using our old equation, half base times height. So we could actually calculate this if we had values in there. But here in our first stage, of course, we have no curve A through to B, so we have impulse being exactly 0. There is 0 net force, or 0 net impulse. But if we now look at B through to C, the grey area highlighted on the curve here, this time, of course, we would describe that this impulse is negative. Now, we can assume in this particular performance with the long jump that that negative impulse is in some way the performer accelerating downwards. So because it's a downwards acceleration, we would consider this to be the knee flexion that's occurring. So we know that as we prepare to take off in the long jump, we actually lower our position by hitting the board, flexing the knee or bending the knee, and our acceleration at that point is actually marginally downwards. So that's why we've got a negative impulse curve. But remember now that we do have a net force. So according to Newton's laws, that must mean for us that the jumper is not stationary anymore, but is accelerating, in this case accelerating downwards. And that Newton's second law, don't forget we must talk about Newton's second law as well, that net force downwards, the acceleration or the rate of that will be proportional to the size of the force acting and in the direction in which that force acts, in this case downwards. So we have that simulated here on the graph. And of course now we actually have a situation where we get back to 0 here and we go into point C. And of course, at this point here, we have the idea that force is now positive, or impulse is now positive. So this point C here is the lowest point of the knee flexion, the knee bend, and we're now starting to drive back upwards, preparing to take off. Remembering, of course, that here, point E is the moment in which the toe leaves the takeoff board. So let's have a think about C to B first of all. We can say here the impulse, of course, is positive. It is above the curve, so impulse is positive in this situation. We can also argue that essentially what we have is a greater reaction than weight force. The reaction force pushing up on the foot is overcoming that weight force. So if we drew that here, reaction force, or GRF, ground reaction force, or board reaction force, would be greater or longer than weight. So therefore we get acceleration upwards or positively. So we are accelerating in a upwards vertical direction. We can also assume between C and D that because of Newton's third law, which again we must reference when we're talking about this, because of Newton's third law, if we have a ground reaction force acting upwards, we have to assume that we have applied a muscular action force downwards, which is equal in size but opposite in direction. But between C and D, we are in the upwards acceleration phase, so we have upwards force acting on the jumper. Now then, D to E is an interesting one. D to E, we still have positive impulse. Just because it is a declining positive impulse, it doesn't mean it's not positive. We are still accelerating upwards, we are just doing so at less rate at this point. So, we are still taking off from the board between D and E, and of course, as I said before, the toe does not leave the board until E occurs. So at the point between D and E, we are looking at the leg extending upwards at the knee, and we are still increasing upwards momentum. We are still increasing upwards velocity of speed, and therefore by doing so, we are increasing the height we'll achieve in the jump, and therefore the horizontal distance that we will actually accomplish. So now we want to have a think quite carefully about how does this, excuse me, that was the wrong thing to do, how did this point E relate to the centre of mass? We know that for a high jumper, because the human body is heavy and therefore has a large inertia, we know that once the toe leaves the ground, the flight will follow what we call a parabolic flight path, because the weight of the body is the dominant force, and therefore we achieve a parabola. So we're interested in where does the jumper at point E position the centre of mass to make sure that the parabola reaches as high a point and therefore as much horizontal distance as possible. Because of course, if the jumper increases the height of their centre of mass or raises their centre of mass to this point, let's look at the impact on the parabola. Well, of course, what we can say here is that the centre of mass actually travels further, covers a greater horizontal distance. So what we're going to say is that at the point of takeoff, point E, we want to raise our centre of mass as high as possible, because during that phase we will actually extend the horizontal distance which the centre of mass travels. So how do we do that? Well, the simplest thing that we can do is to raise our arms. We put our arms above our head. We also raise our non-takeoff leg by flexing the knee, and we actually flex at the hip to bring our one leg up into sort of tuck position. And we also, as a result of that, achieve this notion of raising the centre of mass. You'll even find with long jumpers they actually lift their chin to raise their centre of mass to give themselves a greater horizontal distance, which they can actually apply the greater horizontal distance in which the centre of mass will travel. Don't forget as well, when we're talking about COM, we must define this concept. And the centre of mass is the point of the body in which the mass is distributed evenly in all directions. And of course we can manipulate and change the position of that centre of mass to suit our performance. So as a result, by raising the centre of mass, we actually increase the horizontal distance travelled. Don't forget, it would be exactly the same if we were jumping for height. A high jump, for example, if we raise the position of our centre of mass at takeoff, in this case the parabola will be much taller, but the peak point would be higher because we've raised our centre of mass at the beginning of the jump. Guys, hope that was a useful video for you. Keep looking at this YouTube channel, and there will be others to follow. Thank you very much.